In order to preserve my voice, I'll just speak softer. Okay. So last video we talked about deriving, how we derive all these things all the way, and we talk about why we integrate, because we want to find the velocity component u, right? And then we say that this video we talk about how to apply the two boundary conditions essay. Before I start, I'll just show you something. So let's recap again. For non-pipe system, you apply boundary conditions. You integrate twice and then you apply boundary conditions. This is what we did just now, right? However, if later in the later videos for pipe system, okay, you integrate once and then you apply boundary condition, and then you integrate again and then you apply the second boundary condition. Okay, in this case, we integrate two times first, but for pipe system, you have to do in this manner. Okay, I don't know why, but this is what it is. Whereas for NumPy, you can integrate twice and then you solve for it. So this is just a trick itself. And then you also need to know constant average velocity for fully developed when you're talking about NumPy system. Okay, NumPy system. What we are doing now is the NumPy system. So let's go back to applying the two boundary conditions as specifies. So if you remember, we talked about the boundary conditions. When y is equals to 0, u is equals to 0. So when y is equals to 0, the speed here is equals to 0. When y is equals to a, the speed over here, the velocity over here is same as the plate itself, right? So we can apply the first boundary condition first. Typically when you apply boundary conditions, make sure you apply all the things that are zeros, okay? So you can clear. The purpose of us applying the boundary conditions is actually to solve for the constants of the integrations. Right? If you integrate, you leave a constant, So this is why the purpose of here is to actually to solve for the constants. So this is why we apply boundary conditions. If not, why do you want to apply, right? Because we want to solve for it. So when y is equals to 0, we can just sub in. So therefore, when y equals to 0, hold on now, I use my pen. So this will become 0, this will become 0, and therefore, and then u is equals to 0, and therefore d is equals to 0, right? So this is what it is. And then it's pretty straightforward. Since we know that d is equals to 0, we can apply the second boundary condition. And y equals to a, which is at the top of the plate. At the top of which is at the shaft itself. This is the shaft, and this is turning and turning and turning. Yeah. So u is equals to u, the velocity of the plate. So this u, capital U, is the velocity of the plate or the shaft. Okay. So u is equals to, this is the same old equation which we integrate twice already. So this one is 0 because we found out earlier that d is equals to 0. And now we just sub in your y. So in this case, your y becomes a square. Okay, y equals to a. So the y becomes a. And then to solve for c, okay, you just bring everything. Okay, you just bring this one over here. Actually, this u is equals to u, right? Yeah, just to let you know, I didn't forget to say. So when I bring this over here, it will be minus, right? So there will be a minus sign over here, and then you divide everything by a, so you can get c. So c is this equation. Now you sub back in the c and the d into this whole piece. Then what do you get? Okay, so this u is equals to, I didn't touch anything, right? So let's compare. Okay, I didn't touch this portion over here. So c, I just sub in what we have done earlier, and then y plus 0, right? And then I just rearrange. Okay, so how do I rearrange? I divide by a, and then I multiply in the y. Okay, so this y is over here, uy, and then divide a, and then this y also multiply into here, and then this a can be cancelled. So we are left with del p del x 1 over nu, and then 2, and then a over 2 with the y multiplied inside it, right? So I didn't like anything. And then for the rest over here, we just, because nu and 2, I just put it in together. So this portion over here is this one, right? And then y squared is this. So I'm just trying to shorten them together. And then what I do next is actually to bring this over here. Okay, because as you can see, they have a same similarity in there. Del p del x over here. And then they have y, and they have 2 nu. So what I can do is actually to actually factorize out the del p del x and y over 2 nu, and we have, since you factorize, this one will cancel, so you have y minus a. So this is the equation to solve for the velocity u, okay, a horizontal velocity component u of the oil film, which is the velocity of this thing over here. Okay, so any of this velocity, any layer, okay, any layer, this layer, or whatever layer, can be used, can be described by this formula over here. Okay, so and then it asks us to discuss how u, the velocity u, will be affected by the pressure gradient. So as I explained earlier, it is much affected by the pressure gradient due to certain aspects. Okay, due to this Bernoulli equation over here, although this doesn't look much like a Bernoulli equation to us over here in this manner now. So this is the Bernoulli's equation, and therefore if the velocity is increasing, the pressure actually may drop. Okay, so the negative gradient, as we say just now, as the velocity increases. Okay, this is the pressure one. So at this point, okay, because we are going upwards to, from y equals to 0, we actually use the pen, y equals to 0 to y equals to a, and therefore at this point velocity is actually 0, so the pressure is actually at the max in a certain sense. And as velocity increases, okay, exponentially in a square manner, so it actually may decrease, in a square root manner, right? So as velocity increases, pressure drop, so there will be a negative gradient going downwards, right? So you may, from here you can actually see that I use velocity as a driving term. However, what if the pressure across the pipe, across this section, is different? Maybe at this point the pressure is high, at this point the pressure is low, then there will be a pressure difference also, right? So just to repeat again, because just now I always say that when velocity is equals to 0, pressure is this. When velocity is here, pressure is this, right? So this is using velocity as a explanation to explain why pressure is negative gradient. But what if I use pressure to describe velocity? It's the same thing, right? So if the pressure over here is high, okay, if the pressure over here, hold on a while. So if the pressure maybe not here but rather than at here, if the pressure over here is very high, then slowly the rest becomes lower and lower. So as you can see, your pressure gradient will be at first. So imagine this is the pressure graph, right? So at this point, this one should be the lowest pressure. The lowest pressure already, because this is the highest pressure point. So this is the next condition I'm talking about. So what I mean is positive pressure gradient. Just now I talked about is negative pressure gradient, right, going down. So now I talk about positive one. So as the pressure increases exponentially also, okay, up to this A point, right? the velocity will actually decreases along the y, right? Along this y axis. So at this point, the pressure is low, so therefore the velocity is moving in a very fast speed, right? And then when it starts to decrease, as the pressure increases, the velocity starts to decrease and decrease and decrease and decrease. So typically you exhibit such of a manner. So you have a but however, this is not the case. Okay, in any case, the pressure. So as you can see, all my vectors are going in this direction. But what is shown in my not tutorial but lesson sheet, is that what he drawn. Okay, my lecturer draw is actually what he draw is actually drawing in this manner. So this line is the positive pressure gradient. Actually, not, sorry. This line is affected by the positive pressure gradient. The positive pressure gradient is actually this one. Okay, it's different. This one is the velocity profile. Okay, and therefore it's a little, question mark over here. But nonetheless, this is what I would understand. So this is the pressure gradient that I'm talking about. So how you would be affected? So if the pressure gradient is positive, the velocity of the particle itself will actually move in the opposite direction. Okay, because we have to follow what the lecturer says, right? So it's going in the opposite directions. So while if the pressure gradient is negative, then it's going in this direction. Okay, it's going in this direction. If it's positive, then it's going in the opposite direction. I'll just leave you to think about it, and then if you have answer, just post it in the comment. So I'll see you in the next. So I'll just see you in the next video to talk about the rest of the thing, and then we'll do example 2. And then example 2, I'll just do this part only. The rest I'll just briefly talk about it, and then we can just call it a day. So I'll see you in the next video to talk about the rest. So see you.